Good morning, everyone, and welcome to Greener's latest webinar. My name is Rutger. I'll be your host today, and a special welcome to our power partners and to members of our Easily Emission-Free program. Today, we'll look at advanced setups, how batteries work in synchronizing power assets like generators and renewables, in grid forming and grid following scenarios, with real-life case study examples. Joining me today are our UK manager, Dan Pratt, and battery system specialist Robin Scheick. And this session is for anyone working in construction, events, energy or infrastructure, and our goal is to give you a clear picture of how greener power solutions can play a crucial part in making the energy transition viable by acting as a linchpin in flexible setups. Over the next 30 minutes, we'll cover three main topics. We'll begin with a look at our battery and energy management system. And our EMS is where Greener stands out. Our in-house software transforms the battery from a simple energy container into a smart, adaptable asset that drives advanced setups with complex needs. Next, we'll take a quick look at synchronization, how it actually works and what's needed to get different power assets perfectly in sync. We'll also break down the key differences between grid forming and grid following setups and what each means in practice. Finally, we'll bring everything to life with real-world examples, showing how these principles play out on site. And of course, we would love to hear your questions. You can drop them in the chat at any time, and we'll try to answer as many as we can at the end during our live Q&A session. But before we dive in, let's start with a quick introduction to who we are. Greener Power Solutions was founded in the Netherlands with a clear mission: to speed up the transition to a cleaner, more flexible energy future. It all started with a simple question: how can we move away from diesel generators for temporary power? The answer: mobile battery technology. And that's how Greener was born in 2018. Since then, we've grown from a small Dutch startup into a leading European provider with currently 250 battery units powering construction sites, events, grid support and EV charging across the UK, the Netherlands, Spain, France and the Nordics. But what truly sets us apart isn't just our batteries. It's our in-house energy management system, which optimizes energy use in real time for lower emissions, better performance, and seamless integration with renewables. Across Europe, the energy landscape is changing fast, and that brings new challenges. First, grid congestion. Many projects are facing delays because there simply isn't enough capacity or connection times are too long. Then there is diesel dependence. Diesel generators are still used everywhere, even as the pressure to decarbonize keeps growing. At Greener, we're changing that status quo. We're also seeing rising energy costs. Prices are volatile and businesses need stable, affordable alternatives with flexible financial models that actually work for them. And finally, sustainability pressure. Governments, clients, and communities all expect greener solutions, and they expect them fast. And that's exactly what Greener delivers. Across Europe, our mobile battery solutions are already bridging the gap. Construction sites, we help projects run fully or partly off grid, cutting diesel use by up to 80% while keeping power reliable. And at events, our batteries deliver clean, quiet energy to festivals and outdoor venues, improving the experience without sacrificing performance. And for grid support, our systems allow projects to start even when grid access is delayed, acting as a smart bridge until capacity becomes available. And for EV charging, we enable fast charging hubs in areas where the grid hasn't caught up yet. The road to net zero demands innovation, and battery technology is evolving fast, with more capacity, longer lifespans, and smarter control systems than ever before. At Greener Power Solutions, we're proud to be leading that change. We provide clean, flexible, and scalable solutions that make emission-free operations possible, even for the most complex setups. Now I will hand things over to Robin, our system specialist, and he will take you through the essentials of battery technology and our energy management system. And after Robin's part, then we'll explain how synchronization works, and then we'll dive into our real-world case examples, followed by the Q&A. Just as a quick reminder, if you do have any questions, please put them in the chat.
Thank you, Rutger, for that introduction. I'm going to briefly remind everybody about what the components of our battery systems are and which bits are in there. So we have our 10-foot battery container, which consists of a part of capacity and a part of inverter and electronics. Our batteries do all these things that are on the screen now, 24/7 live monitoring. So it uploads all its measurements directly to the database, which can be viewed. Peak power support, hybrid setups, energy resilience, so backup functionalities and these kind of things. If we look inside the battery, there is the input section, output section, and then the inverter and battery rack itself. Today we will be talking mainly about the input section, battery and inverter side, as we will be talking mainly about the parallelization of these batteries. So that means that we connect the input to the bus and use the synchronization functionality of the input.
Contactor.
Yeah, of the contactor, which is only on the input side of the battery. So that's that. We also then going to talk about the energy meter. Energy meter is a component that we designed ourselves as we require for energy control, so measurements on different locations which are not necessarily inside the battery or inside the energy producing elements. So this is a Pelly container, a Pelly suitcase with a power connection just to measure frequency and voltage, and a couple of connections for our current coils. And these are Rakowski coils, so that means you can open them, put them around a existing installation and close them again. So you don't need to disconnect the cabling in order to place
to thread them through a different type of coil. Yeah.
So you can do if you have a rubberized cable like is here, while it's on load, you can just safely place these.
Makes life easy.
Very much so. All of this is then fed into our EMS. The EMS consists of a watch, which watches all the bits and pieces, and it needs an eye, which is the hardware, to look at all the components. So we have the EMS, which is running on the watch, which is a bit of software, which runs on a bit of hardware, which is this.
The greener eye.
Greener box, the greener eye. So if then the greener eye is in all of our battery systems or in our meters or in anything else, the greener eye gathers all the information, processes that in the watch, and then produces that into Greener Projects, which is our online platform in which all the information should be available for your project.
It gives you visibility of everything that's going on.
Yeah, historically and, obviously not in the future, because that would be an interesting day. But historical data from your entire project will be available in Greener Projects. And we will also produce the reports from this historical data, which is not live, but historical data.
Yeah.
So that's what Greener actually adds to our battery systems.
So Greener Projects allows for energy optimization, because through visibility you can then make improvements.
Which we'll touch upon later in the examples as well.
Sorry, what kind of reports? What
at the end of the project, we can analyze your project. If there could be how much fuel savings we did, and then if you do fuel savings, then you also have NOx and CO2 reductions and all that kind of a thing. So much for what we add as the hard and software, and then a little bit about synchronization and why this is necessary.
Yes, thanks, Robin. I'm Dan, everybody. Nice to see you again. We thought it would be useful to look at synchronization as a topic, because, of course, when we're looking at connecting different power assets to any kind of grid, synchronization needs to occur. So when we're talking about low voltage grids, generally we're talking 400 volts phase to phase, 230 volts single phase or phase to neutral, and all of that's running at 50 hertz, which is 50 cycles per second. So that's the amount of time it takes to make a full revolution, going positive and then negative and then completing, is the speed.
So that would be from here to there.
To that, yeah. And then the voltage is the amplitude, which is the voltage range, how far positive or how far negative that goes in each cycle. Now, of course, the national grid itself, if we're connecting to the national grid, we can't change or control that. That's stuck where
That's
it is.
What it is.
It's a big thing. But when we needed to synchronize a battery to the grid, obviously the battery, when it's in its grid forming mode itself, in order to get that to synchronize, it needs to transition to then follow that grid. So it needs to match its voltage and its frequency to do so.
Yeah, and it does that by measuring the angle difference between the two the two sinuses. So it measures the difference in timing.
Lines the phase angle up before closing a contactor, which it can't do until it's in sync.
Yeah, otherwise you get the interesting green spark part.
Yeah, and of course, just we've gone quite basic here and just looked at one single sine wave. Of course, in a three-phase system, there's three sine waves moving that are all 120 degrees apart. So that's adding a battery, but there might be other power generating assets that we want to add or connect to a grid or a microgrid. So that could be a generator, it could be some solar inverters from a solar farm, or potentially mobile wind or wind turbines, and maybe hydrogen fuel cells could be interesting to try and bring that together. But the synchronization process to get all of this lined up is really important, otherwise nothing works.
It'll be an interesting moment.
So in theory, once we've got all of these things lined up, they're all in sync, so they all become one. They're all following the main grid former in that environment. And once we've done that, that enables us to control power on that grid, so we can adjust power set points, and that's again where the greener EMS comes back into play.
Yep.
So
Guys, can you watch a little bit more in the camera if you're talking?
Yeah. So looking at grid forming and grid following, as we said before, the only thing we can't control is the grid itself, but batteries can grid follow and grid form, so they can run themselves, they can form a grid by themselves. Diesel generators can do the same. They can form a grid and run, but they can also follow a grid, connect to, and then push power into a grid. Mobile wind would follow, solar would follow, as would hydrogen. The reason for mobile wind and mobile solar, they're unreliable energy sources. They're going to be producing a lot of energy when it's windy or when it's sunny, and equally little to none when it's not windy or when it's dark. So that's that. Of course, while we're talking about synchronization and the grid, when the national grid is being used, we do need to look at the regulations that are in place. So we have G99, which is around disconnection under and over frequency or under and over voltage. You can look all of that up online, or there's some information on the slides there that you can review later on. G100 is slightly different. That's more focused on energy import and export across a connection point on the grid. So there's, again, limitations in place that are all different across different connection points. G99 is generally the same requirement. G100 is very specific to each specific connection point. So I'll hand over to Robin to look through what we can do with microgrids, how that works with multiple batteries, and I think starting up with an overview of our standard setups.
Yes. So we've talked about the standard setups before. Note that, so that's the hybridization. So it's a battery and a generator. Peak shaving, in which we peak shave on a grid. So if we have a higher load than the capacity of the battery, we can peak shave on there. Load sharing, in which we, for extra energy, can add another generator. Or grid boost, in which we go parallel on the bus in order to add a little bit of extra energy. These are all single battery solutions. So I wanted to talk a little bit about the multi-battery solutions that we also offer. So then we first create a micro grid, or a disconnected wire system. We have 3 batteries, which then have a total capacity of a total power of 750 kilowatts or 1200 amps.
So based on each container, in this case being the greener container,
the greener container,
250 kilowatts per container, and we can also scale that up or down as far as
indeed.
needed.
And these will then be kind of Lego blocks doing individual parts, and then we can just add more or less
in the right place in the network
when necessary. So we can also you can also kind of scale it up when it's necessary and scale it down when it's not necessary. For instance, if you have a warm period of time, a cold period of time, you've got more heating, you want to gather a bit more energy, and if it's warmer, then you maybe don't need all the capacity.
And just thinking back to the early slides when we were looking at the batteries, those power lock connectors or the Lytton connectors make the ease of unplug, replug really flexible.
Absolutely, yeah. So this is the basis. Of course, as soon as the load starts using energy, the batteries are depleted at some point. So we need more. We need to gather the energy from somewhere else. We can use renewables. If we use renewables, we need to control the renewables. So that means that we need to wire them in somehow to our batteries and then control them with our EMS in order to determine when the renewables need to produce more energy, or if they are producing more energy than we can store, to curtail them back to less energy. So and that will result in matching the energy produced by the solar or wind, by the renewables, to the load that is there. If that still isn't enough, we can add other components. So that will be could be hydrogen generators, diesel generators, gas generators, guy on a bike, I don't care. But as long as it's also controllable from our EMS system.
The guy on the bike might be a challenge there.
You need a lot of them. What we could also do is stick a load of batteries on the back of a trailer, and in that way cart the energy from a different place into the site. There's a couple of examples in our portfolio in which we've done that. If you want to know more about this, please ask in the question.
I guess the nice thing there is taking a grid connection off-site, charging batteries up, and then discharging those batteries into the microgrid.
Exactly.
Doesn't necessarily need control from the EMS there, as long as you don't overfill the batteries when you're doing the energy delivery.
Yeah, it needs a bit of organization.
Yeah.
But it's very, very, very possible to do. Okay. So that's so then we have our basic system running.
Grid forming.
Yeah. And if there's no grid there, we will have to make the grid ourselves. So that means that the batteries are in a grid forming mode. We are not following anything else because we are the strongest part there, and we are controlling all the other bits to come on, to be switched on and off as the energy demand needs that.
So energy optimization being the key there. So looking
Absolutely.
at prioritizing renewables over certainly fossil.
And then going between, do you want to cart it in, or is the fossil still there?
Flexibility.
Yeah. So the interesting part comes when the grid actually comes into it. So we'll first talk about a large grid connection. If there's a large grid connection, we will feed it directly onto the main coupling point, or I always call this a bus, main bus. And as the grid is doing whatever it wants, we can only monitor it. So we place a meter on those lines coming into that main bus.
But the second that large grid connection comes in, or if it's there already, then naturally the batteries they can't form that grid anymore.
No.
Because there's the grid that we discussed before, we can't control that.
No.
We then have to follow it.
Exactly. So then we're going into a grid following mode. Why is that? The main reason for that is that if we're in grid forming mode, we use the frequency to control the entire grid. And if we are connected to the main to the national grid, well, with our 750 kilowatts, we're going to do absolutely nothing in changing the frequency against the national grid, which is how many gigawatts of energy there. So we just monitor the power flow and then add or subtract power flow to respect the limits which are on the grid grid connection that we're monitoring right there. So what if there's then a small grid? There's still a significant amount of energy that we could gather. So but we do not want to be able to overload by step loads that small grid connection.
You don't want to follow that grid connection.
No.
Because you'd be reliant on it.
Absolutely.
Yeah.
So if, for instance, we have a 50 amp grid connection and a 1000 amp load, that's out of sync. If anything happens at the load side and it's slightly faster than you expected, we're going to trip that input that grid connection, and thus lose whatever we are following.
Of course, looking at the G99 regulation in that sense, because we're grid following, if the grid did trip, the batteries would have to open their contactors and turn off.
And everything needs to switch off.
Yeah.
So the solution that we've designed for this is what we call a grid sync, which consists of a AC, DC, AC inverter, and then breaking that frequency dependency on the national grid. This then is also controlled by our EMS. Because you can imagine that if this is only a 50 amp grid connection, that's enough to fully charge these. If this is a 50 amp grid connection, that's enough to charge all of these batteries once every day.
If there's no load.
Yeah. But it's enough energy.
Yeah.
So one of the real world examples that we have is St. Clair School, and Dan's going to talk to you a little about it.
Thanks, Robin. Yes, so St. Clair School was a project that we ran for about 18 months, starting in 2023. It was a school that had a rack problem. So some of the classrooms, they had to be demolished, meaning that they needed to provide some temporary classrooms for the kids to still go to school.
To the small kids, right?
Yeah, I think it was a high school.
All right.
Not that that's necessarily relevant, but anyway, the school itself, had the temporary classrooms fitted, but there was a power shortage from what they had on site available. They couldn't power the temporary classrooms. Well, naturally, I think temporary classrooms probably require more energy than an installed one because they're less insulated and so forth. So we'll run through kind of the challenge. So the challenge was really that on the site there was a 1,000 amp max capacity grid connection, and the existing building, so the rest of the school that was still functional, had a peak requirement of 800 amps. But the temporary classrooms required 400 amps, or around a 2 megawatt hour energy consumption over a day. But that meant that just to be able to provide the peak power, we ended up with a shortfall of around 200 amps, which presents a challenge. You couldn't just connect the classrooms to the grid because there's every chance you'd overload that connection. So we did this quite simply, and this is one of our simple setups. So this would be traditionally considered a load share setup, or one of the ones that we looked at in the past webinars. Simply, we take a 200 amp grid connection, we peak shave that connection on a battery, and then we connected a 300 kVA generator to the output side in a grid following mode that would enable us to get more energy into the sort of the battery if the load is greater than we can possibly get from the input connection. So looking at the power trends on the site, you can see at the top here we have the state of charge, and the state of charge, we only start using the energy in the battery during times that the load overtakes or oversteps the 200 amp input current limit that we set in that case. So we don't use any energy from the grid while the load's under 200 amps. We only start using energy from the battery when the load overtakes that mark. And that's when you start seeing the battery discharge. However, when it was warm, there wasn't a huge amount of energy being consumed from the battery, certainly anyway, which meant we only discharged a few times during the day. And of course, when the school closed, there was an opportunity for the batteries to recharge because the load dropped. We still had that 200 amp input available, and the batteries were able to recharge again here without needing to run any additional energy producing assets. However, when it got cold, the load on the site, the load requirement went up. All of the electric heating came on, so the school itself were getting through a lot more energy in the temporary classrooms than they were during the warmer months. And that resulted in the generator having to run. So this graph here is our converter power, or the inverter power, what the inverter's doing. So when the battery actually depleted to a lower set point that the green at EMS is monitoring, in this case it was set at 25%. When the battery reached 25%, it started that fixed export generator, which then allowed the battery to recharge to 75% very, very quickly. And you can see that on the inverter when it swings into the positive, so charging, away from the negative or discharging.
Yep.
And you can see that happens very quickly on a few occasions where the energy is low. So that really gives us some good flexibility, and we were only calling the generator when necessary. We're gathering everything we can from the grid. However, after the project ended, we did analyse the project and we looked at what we would have done differently. So what we would have done differently would have been to have gone to a more advanced setup. And that would have involved going into a grid following situation with an energy meter, because that would have meant that we could have taken a full 400 amps worth of cabling from that grid connection, measured it, and then allowed the battery to adjust its set point either side of 400 amps, which in this case would have meant that generator that was sitting up here was no longer needed.
And we could have scaled up easily in the wintertime.
Added an extra battery.
More capacity needed.
Yeah.
And scaled down again when the capacity was not necessary.
Absolutely. So just looking at the results here, I mean, the backup generator was needed for around 4% of the energy production over the 18-month period. But from the data that we gathered, we were actually saving around 20,000 litres of diesel per month based on a comparison which would have been a 500 kVA generator running 24/7. So, of course, diesel saved, also produces emissions saved. And on a school, you don't want polluting,
Mm-hmm.
noisy, so silent running was another thing. Of course, 4% of the time that generator
Yeah.
did have to produce some energy, but actually our improved setup would have negated the need for that altogether.
Yeah. And 19,500 liters of diesel times £1.80, I think it's nowadays. For,
Yeah, considerable financial reduction as well. So I'll hand back to Robin for our next case.
Festival on solar energy. So this is one of the most interesting setups that we did this year. We had a festival which has a enormous solar farm around it, and we used 6 batteries to back up a main line for the sound and lighting, and 5 batteries to back up to harvest the solar energy during the day and discharge that when it was necessary during the evening. So what does that slightly look like as a setup? So this is the fixed installation which is there. There's a meter fixed into the 100 kV grid connection, transformer, because it's useful to not do that every year at the 100 kV line, and then the 5 megawatt solar park and a small tag-off transformer somewhere in the middle. And the question was, can we then feed into 2 courtyard lines and then stage line? So on the stage line there would have been sounds and lights. And the question from the customer was, can we please make sure that the main stage, whatever happens to the rest, always stays running, and it doesn't really, and if the courtyards are out of power for a few moments when something goes horribly wrong, that's not such a big problem. So we said, that's fine. We'll put a battery in standard peak shave mode onto the main stage, and that's more than enough.
So in that instance, that battery that's sitting there is going to grid follow
Yes. So
when it's in peak shave mode.
yeah. So
But if the grid were to fail here,
it'll immediately pick up.
it would revert immediately to grid forming mode, and that happens very, very quickly.
4 milliseconds.
So the stage wouldn't have noticed
Not at all.
any change in power output.
This happens, and then that break of the power flow and then the changing from forming to following happens every single time you do a cycle.
Yeah.
On a generator or something else. So that's the standard. The interesting part of this whole story is the 5 batteries feeding into that same distribution panel just after the transformer feeding into the courtyard and the battery that's doing the peak shaving.
So those 5 batteries were needed to do what?
Just capacity storage. Capacity storage mainly. And if they are there, they need to be controlled by our EMS. That is then gathering the energy measurements coming from the main connection, because that has a limit of 0 in and infinite out. So we're not allowed to draw any energy from the national grid here, but we're allowed to put any kind of excess energy back into the grid, which is the bread and butter of the solar park. Their bread and butter obviously is selling this energy to the grid. And then the other limit is that the transformer, which is there, has a limit as well of being 500 kilowatts back and forth.
So not enough to power the site itself.
Well, definitely not at night, because the EMS will take the most conservative measurement. At night, when the solar farm is not producing any energy, and we're not allowed to take any energy from the grid, we will have to insert that energy from our battery systems.
And deliver that to the load.
Yeah.
Yep.
So that means that during the day, the energy will be going here, and whatever's the excess goes into the grid. And when the grid and when the solar is gone, the energy will be so during the day the energy goes this way and that way, going from the solar directly into the batteries and the courtyards and the stages. And when the solar goes away, then the limit, the most conservative limit, is the 0 from the grid. So that means that these batteries will be discharging into
the load and the peak shaver for the main stage.
Yeah, because the peak shaver in that point of time is just a part of the load. We try to keep this battery as full as we can, so that if anything happens, that will take over. If that would have happened, we would have been able to disconnect the main breaker at the top of the transformer on the LS rack and put all of these batteries into a grid forming mode.
So although a main power cut to the 2 Ford courts, there's actually a method to get those 5 batteries back on in grid forming and reinstate power very, very quickly.
Within 10 minutes.
Yeah.
And
that could also be done remotely.
Yes, there's a couple of so there will be guys there doing some of the manual switching. There's main switches which need to be manual done, and then the system changing we will be doing.
But if it was a permanent installation that you were looking to do something similar to this for, you could remotely automate some of that with contactors and motorized breakers.
Motorized breakers.
Yeah.
Most transformers do not have a motorized breaker in them standard.
Yeah.
Just having a look at the squiggly lines from the graphs, the total load, which you can see here, there's there are 3 show days, and there's the startup of the coolants, and then there's the load in, and then the load out again. If you can see here, during the show days, it's about 3,500 kilowatts at peak, and then when the load out starts, it drops down again, and when the load in starts, it ramps up. And then if we then look at the energy provided by the transformer, so
the solar panels,
and that's the solar panels, but we're measuring at the transformer. That's the green line that happens here. You can see that it ramps up when the sun comes up, stays at its limits, that it's there, and if it's full, it just passes through the energy, and the batteries are not doing anything, and then it doesn't take any excess energy because the batteries are already full. Well, and then you can see here that the solar ramps off, but the load stays on, so that means that the batteries have to make up the difference.
So some people would refer to this as solar sponging.
That's a new word I've learned today. Solar sponging. Yes, energy. But that's exactly what you do. You just gather the energy, you harvest the energy during the day, and then use it when you need it. So that will be here. The yellow line is what the battery is making up the difference between the production of the solar and the load, and what the load demands at that specific point in time. And then just to give you a little reference, here is what the solar was actually doing in this period of time. Note that on the first show day, it was obviously a very bad sunny day. So they needed to switch off some coolant or temperature dependent machinery to save some energy. And that's what you can also see here, and that's as this is the state of charge of the batteries against the energy usage. That first day we went very deep
because there's no sun.
Because there wasn't enough sun.
Yeah.
What does that mean in results? If we would have needed to generate the kilowatt hours only via a generator set or generator sets, we would have burned around 7,000 liters of diesel, which would have resulted in 23 tons of CO2 and 170 kilograms of NOx.
Which, of course, for a week-long or a weekend festival doesn't sound like a huge amount, but if you were to apply the same principle to a permanent installation, that very quickly ramps up. And
this is every week.
Exactly. Yeah.
It's every week, right? And especially if you're then looking at the days in which on the festival days itself, when the load is very high, this skyrockets.
Yeah.
I think that was it for us for the real life examples, and I would be very interested in the questions. Rutger, what are the questions that we got?
Yeah, thank you. That brings us indeed to our Q&A. For now, I see there's just one question. So
wow,
if you have any,
we must be very good at explaining
this. Ask them. I guess it's a compliment, right?
Yeah.
But someone would like to know what if you could once again explain the difference between grid forming and grid following.
Right. So I guess we'll go back to the slide all the way at the beginning. Let me just grab that. So the difference between a grid following system and a grid forming system is that if you're following, it's the way that we connect the main grid into the entire microgrid. So if it's a large grid, we will tie that directly into the distribution box while measuring the grid connection. Oh, I'm pressing all the buttons.
I think maybe the
Yeah.
difference.
So the
would be-
difference is the way that we connect the main grid, and as the technology to do in parallel systems to distribute the energy over the batteries is over frequency. So we need to make a distinction between when we can control the frequency on the grid on our side, and when we cannot control the frequency on our side. That's because it's a droop control system. This is the same way that the national grid also works. So you can imagine if we want to do our little small drooping thing, but the national grid is doing its own droop thing, but then at gigawatts.
It's exactly the same. I mean, you might have a power station in the southwest of the UK.
Yeah.
That's grid following the national grid, and then there's another power station somewhere else in the southeast maybe. They all need to synchronize, and then they end up following what is everything else.
Yeah, so that's the droop control, because you can imagine that if you have if you follow the voltage over a line, that is the voltage is dependent on the loss over that line. So there's impedancy and resistance that has an influence on that. The frequency throughout a grid is the same regardless of distance. It cannot change. So if you would if there's a large problem in Spain, they would know in the Nordics within a few microseconds, because they would see a bump in the frequency. All the other things would start to adjust immediately. And this is the same technology that we would use for our microgrid as well, to balance all the energies out. So if we're doing that, if we're trying to use our microgrid technology while we have the national grid connected, that won't work. So that's why that's why when we're doing our microgrid onto the main national grid, we use a grid following mode, because you pick the strongest thing within your assets to be in control of that frequency,
And
which would be the national grid.
If you break it down and look at like a single diesel generator, if you switch it on, it has to rotate at 1500 revolutions or 50 hertz. And it has to form a grid. Without that grid, without that frequency being generated or rotating, without that voltage being present, you can't consume energy from it. So that has to be there. Something has to create it. And that could be, and that's where we use the phrase island. So an island generator does that. It's grid forming itself. We do exactly the same with the batteries. We can grid form, and that's switch the battery on. The inverter then creates the AC, the makeups of the AC, which is the voltage and the frequency, to enable us to draw load from those devices.
Yeah.
Right. Yeah, I see a lot more questions coming.
Oh,
in
good.
now, so I don't have,
I was trying to fill 10 minutes with that one.
exactly.
So,
I thought you were doing that. So yeah, let's go on to the next one. Could you discuss a bit your battery swapping mechanisms with Into the Great Wide Open?
Right. So Into the Great Wide Open, which is a festival that we talked about in our Dutch webinars a few versions ago. What we did there, we had a grid connection 700 a kilometer away from where the energy was actually needed.
we did exactly the same in the UK for the Lido Festival.
For the Lido
as well.
Festival, yeah. So that's the same, right? We have a grid connection, just a little too far to run cables, or you have a little small couple of patches where you have an energy need. So at the Lido Festival, we had a single battery being charged at the grid connection and then traveling to all the different places that needed energy.
So on the areas of the site where power is needed, you'd create grid forming microgrids with other batteries.
Little islands.
On a trailer, another battery that's going to the grid connection, recharging, and then it comes back into the site and discharges its energy into the microgrids on the ground, as you can see going on with our little truck here.
Yeah.
It travels off site, recharges this guy, he comes back in and discharges the energy into the microgrid.
Yeah, and then that gets that, and then so the energy coming in here will be dispersed amongst the assets which are there. Obviously, the energy will first go. It'll try to. The batteries will ramp down if there's energy coming in, and then if there's excess energy available, they will charge themselves with whatever excess energy is available. So the idea, one of the key components here is that the energy being delivered, or the power of the energy being delivered, needs to be more than the load is in order to charge the batteries, or you just
you slow down the
discharge.
Yeah.
Right.
So there's 3 main places where we did this. We did this at a drilling facility in Den Bosch in Holland, in which we had 4 trailers going back and forth over the motorway for a drilling company. We had the Into the Great Wide Open, where we had little places, and we had the Lido Festival in Great Britain, in which we've done this.
Great. Yeah. Okay. Sorry to interrupt you here, but we have 2 more. Why is there multiple sets of power lock connectors we used? Why is there multiple sets of power lock connectors? We use multiple batteries, but only 1 set of power locks.
So if we go back to when I explained the battery basics, I'll just grab that picture here. I talked about the fact that here there is, we're only talking about the input side of the battery. So that's this input side of the battery. If you would use it in the normal mode.
So single container.
So these are all rated for 400 amps or 250 kilowatts, which is the maximum of the inverter. And if you look very sharply, you will see that this is
they're power lock drains.
Drains and sources. Because the sources, that's this double row on the outside, are all for the output side of the battery. And as we are connecting in these multi-setups, parallel setups, all to the main bus, and that from there we disperse the energy further along the line, we're only the maximum power of the battery is only this 400 amps, 250 kilowatts. So a single run is sufficient.
It's the same if
per
you were
system, right?
Connecting multiple diesel generators, you would send 1 set of cables to a common bus from each generator.
From each one, yeah.
And we do the same because it allows flexibility. The only difference really with the battery is we can charge and discharge, whereas a generator is only going to produce energy out.
All right. Next one. What is the maximum amount of battery systems you can combine?
Theoretically, there's no limit. Does it get unstable at some point? Probably. We've done 10 in a cluster now, no problem. In grid forming, we've done 10.
Yep.
In grid following, we've done 20 at once. Without a problem.
Following, that really should be infinite.
That should be infinite.
Because you can just keep scaling that. Yep. Grid forming, that's when, as you said, we've done 10 very successfully.
No problem.
But that is where, obviously, we're having to form the grid there. So there are more intricacies involved.
Yeah, and intricacy is, of course, going to be that every individual thing has its own controller. And at some point, it'll become, the controller needs to be adjusted to become stable at the larger scale. But that's just settings and testing.
Yep.
All right. Thank you very much. That brings us to the end of today's session. Thank you so much for joining our 4th UK webinar, Advanced Setups. Special thank you to our power partners for being with us today. We really appreciate your time and engagement. Before you go, we'd love to stay in touch. Just scan the QR code on the screen to sign up for our newsletter and get updates on upcoming webinars, industry news, and insights from the Greener team. So thanks again for spending your time with us, and we look forward to seeing you at the next one. Bye.